Okay, let's go ahead and get started. First things first, sorry for missing class on Monday. I was not deathly ill. I was rather ill, and it was best for everyone concerned that I didn't show up. Hopefully you all got my email and didn't come in early on Monday. Or if you did come in early, hopefully you found the brisk morning air invigorating and good for your health. Okay, so sorry about that. In general, please do check your emails. I do send out course announcements by emails, sometimes, unfortunately, at last minute. Is there anyone who did not get the email announcement canceling class on Monday? If you did not get that announcement, that means that I do not have you on my course email list. So please send me an email to let me know. Other order of business, I would like to schedule a makeup class. I have my lectures on a pretty tight schedule, so missing one lecture puts everything out of whack. So I'd like to schedule a makeup class on the sooner side. I was thinking Tuesday, Thursday afternoons seem to be the time when most people are available. So would tomorrow afternoon at 4 be an acceptable makeup class? Yes.
It's not good for me.
It's not good for you. And it's not good for you, if I remember correctly. Is that correct? Or am I misremembering? Thursdays at 4?
Thursday?
Yeah.
Thursday,
Before 4. But 4 would be okay? So there's one person. So if I were to schedule a makeup class to make up for the class that I missed Thursday at 4, you couldn't make it? Are you the only person who couldn't make it? Unfortunately, that might be the best that we can do. Tuesdays at 4 is the other possibility. And there are 2 people, however, who can't make it for Tuesdays at 4, if I remember correctly. So the alternative would be to do a one-time makeup class sometime in the evening. I'm free today at like 5:30. Yeah, I'm free at 5:30 today. Anyone want to do a makeup class today at 5:30? How many people couldn't make it? A lot of people couldn't make it. Okay, well then, with my apologies, maybe we'll have to schedule a makeup class tomorrow. Tomorrow, which is to say Thursday. What is the date of tomorrow? It depends on what today's date is. The 20th?
Tomorrow's the 20th.
Jesus Christ. At 4 p.m. Would 4:30 be better? Could you make it if it was 4:30?
Sure.
Yeah?
Yeah.
4:30 is okay, but 4 is not okay?
4 is fine. It's just not great.
Okay. There's a difference between not... Okay. I won't give another lecture. Okay. Yeah, so I'll figure out a room for that right after class and send you an email. Anyway, hopefully you don't mind a makeup... Well... Let's put it this way. I have 27 lectures and 27 lectures worth of stuff to get through, so I'd prefer not to skip any of them. I have about 1 lecture's worth of wiggle room, but I'd prefer not to lose that wiggle room within the first 2 weeks of the semester. Second announcement regarding the second problem set. I was going to have it due next Tuesday, but I decided to give you an extra week for the next problem set, just because... I missed a class Monday, so you would you really need the next 2 lectures worth of material to do this problem set. So that would only give you 4 days. So I figured why not put us all in a slightly more relaxed schedule. That way, for the rest of the semester, I'll be a little ahead of the game when it comes to the coordination. The problem sets are tightly coordinated with the lectures, so this will give me a little bit more wiggle room with regards to the scheduling of the lectures with respect to the problem sets, if you know what I mean. That probably doesn't make any sense whatsoever. It makes sense to me, though. Anyway, the upshot is that this problem set is due not next Tuesday, but the following Tuesday. Third announcement. So as I said in the very beginning of the semester and also in the syllabus, I don't accept late problem sets unless an extension has been obtained beforehand. Several people either did not hear me or misunderstood me and turned in late problem sets anyway. In the spirit, I'm a magnanimous, beneficent person. So in the spirit of that magnanimity, I'll let it slide this one time only. But please take me seriously when I say that I don't accept late problem sets. You know, I'm handing out the solutions. I'm handing out today. You know, right after the problem sets due. And so please take the problem set deadline seriously. If there is a problem, and if you genuinely need an extension for some reasonable reason, that's totally fine. You just have to ask me, or one of the TAs beforehand. So in the future, you know, I'll be magnanimous today, but in the future, expect me to rule with a fist of iron. Okay, enough administrative stuff. Let's do some physics. Yes. I do, as I said, I will find a location for it as soon as this class ends. I don't know if the room is available. If it's available, I'll book it. Generally speaking, the university has draconian and onerous procedures for booking their rooms. So I'll probably have to, most likely it will be in room 326, which is a room that I can book in 5 minutes as opposed to the several months it would take me to book this room. Yes?
Did you talk 232?
What's that?
Did you talk 232?
So let me tell you, the way that, not that this is a particularly interesting thing to you, the way that it works is there's certain rooms administered by the university and certain rooms administered by the department. If I want to book a room administered by the department, I go to Louise and I say, can I have this room? And she says yes. If I want to book a room that's administered by the university, I have to talk to some faceless pencil pusher in some administrative building, and it never works. So, roughly speaking, the only rooms I can book are the piano room, the bell room, and 326. Okay. So, most likely it'll be in 326. If 326 is booked, it'll be either in the, it'll be in one of the rooms, it'll be somewhere in this department. It'll be a surprise. Okay, good. Okay, enough administrative stuff. Let's talk about some physics. So, last class, we used the equivalence principle to argue that the proper description of space-time in general relativity is that of a manifold, and in particular, space-time is a particular sort of manifold. So in particular, it's what I'm going to call a pseudo-Riemannian manifold. And this class, and for the next couple classes, we will focus only on this word manifold and understand exactly what that means before then delving into the various geometric structure that this manifold has, which is responsible for the term pseudo-Riemannian. So what does it mean that space-time is a manifold? It means that points in space-time, i.e. events, can be smoothly labeled by a coordinate system which is to say a set of four functions x mu, where mu is an index that runs from 0 up to 3, which smoothly labels points in this space-time. Now, in general, of course, there could be many different coordinate systems that one can use to label points in space-time. And one can, of course, write these different coordinates as functions of one another. So two different coordinate systems are related by a coordinate transformation or a change of coordinates where, for example, you could write, if you have two coordinate systems x mu and x mu prime, where the prime here denotes a different set of four coordinates that label points in space-time, then in regions of space-time where both of those coordinate systems are well-defined, you could write the x mu's as a function of the x mu primes, and likewise you could write the x mu primes as functions of the x mu's. So this is, in fact, something that should not be terribly new to you. So, for example, In the case of the plane R2, two of your favorite coordinate systems are the Cartesian coordinates xy, and which those would be, for example, the x mu coordinates, and the polar coordinates are theta, which you could call the x mu prime. Now, there is a little bit of notation that I introduced last time where I typically use Greek mu indices to refer to space-time, which runs from 0 up to 3, and I'll use Roman indices to refer to Euclidean spaces such as the plane or 3 space. So maybe what I'll do is I'll call these I indices rather than mu indices, where I here runs from 1 up to 2. And likewise, so does I prime. And then these coordinate transformations are just the usual writings of the Cartesian coordinates in terms of the polar coordinates and vice versa. So, for example, writing xi as a function of the xi primes is the two equations x equals r cosine theta, y equals r sine theta, and the other inverse coordinate transformations are given by the inverses of these formulas, writing r and theta in terms of x and y. Now, you might be asking yourselves why I'm being so pedantic about spending our time discussing the theory of coordinate transformations, which is probably something you've not thought particularly hard about up until this point in your lives as physicists. But the reason is that we wish to write the laws of physics in a way which is independent of the coordinate system that one uses to write down those laws. So, for example, you can write down Newton's laws in Cartesian coordinates or in polar coordinates. The functional form of those laws of motion might look different in those two coordinate systems, but the physical content of those laws and the outcome of any experiment based on solving those equations of motion will, of course, not depend on whether one uses Cartesian or polar coordinates. And what we need to do then, yes?
Just a notation question.
Yes.
If I, like, xi runs from 1 to 2, xi prime runs from 1 to 2, so if I write, say, x2, what do I mean?
If you write x2, you mean the second of, you mean y.
So,
x2, yes.
How do I distinguish if I want to write x?
You would write x2 prime. Okay. Yeah. I guess I'm being, I guess, let me erase that sentence if that makes it a little clearer. So, if you wish to view that as a symbol, where I runs from 1 up to 2, and view this as a symbol where I runs from 1 up to 2. Yeah, I probably shouldn't have written 1 prime runs from 1 up to 2. You see what I mean here? So x1 is x, x2 is y, x1 prime is r, x2 prime is theta. I probably shouldn't call 1, I could call I prime, 1 prime, and 2 prime if I wanted to use a slightly perverse notation. But let's not do that. Yeah, hopefully my answer, that clarifies any confusion. Yeah. Good question, yeah. Thank you. Any other questions? Yes.
Isn't 0 or I 0 take
Excuse me? Sorry, I didn't quite catch that.
Isn't I 0 base or
0 base? I'm sorry, I don't understand.
0, 1, 2 instead of 1, 2?
So the notation that I'm using, this is something I touched on last class. The notation that I'm using is that, in general, of course, one can consider, it doesn't matter whether you take your indices to run 0, 1, 2, 3, 1, 2, 3, 4. As long as you're consistent, it's just a matter of notation. And so the notation that I'm going to stick to universally throughout this class is that Greek indices, mu, nu, and so forth, will start from 0 and run up to some number, which is the number of spatial dimensions, which thankfully in this class is usually 3, or less if we want to consider simpler examples. And 0 is time. And Roman indices I, J, and so forth will start at 1 rather than 0 and run up to however many spatial dimensions we have, which thankfully is going to be at most 3, unless we take it to be smaller to consider a more simple example. In general, of course, there's a sense in which it's not fair to say that 0 is the time direction, because as you know, space and time are treated in equal footing on relativity. So the fact that one of the indices is 0 and the rest are positive is related to the fact that there's one time and a bunch of spatial directions. But of course they mix, and they mix under coordinate transformations, which is what we're going to describe. So yes, good question. Any other questions? Excellent. Please feel free to interrupt, ask questions as often as you like. Okay. So our goal is to write the laws of physics in a way which is independent of the coordinate system that one uses to write them. And so far in your lives of physics, in your lives as physicists, you've been able to do this without thinking particularly hard. You know, when you took your vector calculus class, essentially what you were learning to do in the class was precisely this: to write laws of physics in a way which are invariant under the rotations, which are the fundamental symmetries of the plane or of three-dimensional space. Now, however, space-time is more complicated. It's four-dimensional. It's not even necessarily a flat space. So we're going to have to think much more carefully about what it means for the laws of physics to be independent of coordinate systems. And this will lead us to the subject of tensors, and it will lead us to the conclusion that the laws of physics, no matter what they are, must be tensor equations. And so that is the goal that we will lead up to this and next class. And then after that, we will understand what sort of equations can be written down using tensors. So the first thing that we need to do when thinking about how to write down the laws of physics in a coordinate invariant way is to first understand how various quantities transform under coordinate transformations. So if we want to write the laws of physics in a way which is independent of the choice of coordinate system, then obviously a good way to start is to start by looking at the various quantities that appear in our laws of physics and ask how they change when we do a coordinate transformation. Now, this is a course on relativity. So clearly, the appropriate place for me to start then is to look at the fundamental object in the theory of special relativity, which is the line element that one uses to construct the invariant interval, or the proper time as measured by some observer moving on some world line through space-time. So the formula for the line element is given by ds squared is eta mu nu dx mu dx nu, where eta mu nu is the constant matrix with entries -1, 1, 1, and 1 in flat Cartesian coordinates. So when we make the coordinate transformation, where we try and write the coordinates of flat Minkowski space in some other way, so let's say that we wish to make a coordinate transformation, and instead of writing everything in terms of the flat Cartesian coordinates x mu, we write them in terms of some new coordinates x mu prime that are a function of these x mu's. These could be spherical coordinates, they could be polar coordinates, they could be ellipsoidal coordinates, they could be boosted coordinates, whatever. So we need then to ask what the line element looks like in this new coordinate system. Well, we need to first understand how those infinitesimal displacements dx mu look in this new coordinate system. So this is a problem which might be familiar to those of you who did the problem set that was due yesterday. So let me just briefly explain to you how it works, since many of you probably worked it out in detail earlier this week. So under an infinitesimal displacement where x mu goes to x mu plus some small displacement dx mu, you can then ask how x mu prime transforms. X mu prime can be regarded as a function of the x mu's. And so x mu prime will then go to x mu prime of x mu plus dx mu, which we can then Taylor expand to linear order in this displacement dx mu. And so it becomes x mu prime plus the linear term in the Taylor expansion, which will involve a sum over mu from 0 up to 3, because we're Taylor expanding in 4 variables. So there are 4 linear terms in that Taylor expansion. And the coefficient is dx mu prime by dx mu, and that's multiplied by dx mu. And again, I'm using Einstein summation notation here. So I'm summing over mu, and mu prime here is a free index. And this, of course, is just the linear term in the Taylor expansion of x mu prime evaluated at x mu plus dx mu. And this quantity here is what we call dx mu prime. So dx mu prime is equal to dx mu prime by dx mu times dx mu. And likewise, the inverse of that argument, or if you like the same argument with mu replaced by mu prime, says that dx mu is equal to dx mu by dx mu prime times dx mu prime. You can see the beauty of the Einstein summation notation. If we had to write those stupid sigma symbols everywhere, we'd never get anywhere in this class. Okay, so I could take this formula here and plug it in up here to the formula for the line element. And what do you get? You get ds squared is eta mu nu dx nu, just rewriting that formula above. Now plugging in our formula for dx mu, this is eta mu nu dx mu by dx mu prime times dx mu by dx mu prime times dx mu prime dx nu prime. And so one can regard this quantity here that I've written in the parentheses as some function of x mu prime and x nu prime, which is now the metric of flat Minkowski space, but written in the primed coordinates. So this is the expression for the metric in primed coordinates. So what we have seen here is that the metric of flat Minkowski space transforms under coordinate transformations. And it transforms in a very particular way. In particular, for each one of the lower indices in the metric eta mu nu of flat Minkowski space, we pick up a factor of this Jacobian matrix right here. This is characteristic of what is known as a tensor. And in fact, this statement that the metric of flat Minkowski space transforms in this particular way under coordinate transformations is what is known as the statement that the metric is a 0,2 tensor. And so that is a statement that I will expound on in greater detail this and next class. Before I do so, let me see if there are any questions. Yes?
Z is still minus 1, 1, 1, 1?
Eta, I guess, or you can call it Z if you like, I don't care. Or Z, excuse me. Yeah, eta is minus 1, 1, 1, 1. But now, if you wanted to write, you could write this, for example, as eta mu prime, nu prime. Usually we use the symbol eta to refer to the constant. We might use the symbol eta to refer to the constant matrix, and we might use G to refer to some more general form for the metric. So eta mu nu is the constant matrix. But if we were to write a symbol like eta mu prime nu prime, that would refer to the metric in this new coordinate system, where it might not be a constant matrix. Well, it depends on what coordinate system you're using. So let me give you a very simple example. That's a great question. So let's consider the case of the transformation from Cartesian to polar coordinates. And let's just do things in R2. Okay? So the transformation, so x is equal to r cosine theta, and y is equal to r sine theta. And so the question then is, what is the line element dx squared plus dy squared? Remember, this is just the thing that you use. This is just Pythagoras' theorem, right? Ds squared is dx squared plus dy squared. So what does that look like in the polar coordinate system? Well, we need to evaluate dx and dy. This is something that hopefully you got a little bit of practice with in the problem set due yesterday. So to compute dx, well, what is that? That is the derivative of x with respect to r times dr, so that's cosine theta dr, plus the derivative of x with respect to theta times d theta, so that would be minus sine theta r d theta, with similar expressions for y. So dy is sine theta dr plus cosine theta r d theta. Now, in your head, of course, so the best way you're going to find yourself doing this computation a lot over the course of this semester. So let me tell you the right way to think about doing this computation. The right way to think about doing this computation is to think of D as a differential operator. In fact, it is a differential operator, as we'll see. So you think of D as a differential operator, and it obeys the usual rules of differential calculus. So dx is d of r cosine theta, and d of r cosine theta is dr times cosine theta plus r times d of cosine theta, and by using the product rule for derivatives. And what is d of cosine theta? D of cosine theta is the derivative of cosine theta times d theta. That's the chain rule. So you're instructed to regard d as a differential operator, just like the usual derivative. And in fact, d is a differential operator. It's called the exterior derivative. We'll meet it, maybe not this lecture, but next class. Or maybe not next class. No, maybe next class. Yes. So then it's a straightforward exercise to go ahead and plug these guys in to this expression here. And the answer that you get is a rather simple one. All of those horrifying sines and cosines will combine together to either cancel or give you sine squared plus cosine squared equals 1. And you get the expression for the metric and polar coordinates, dr squared plus r squared d theta squared. If you don't know that formula for the metric of flat space and polar coordinates, it's worth remembering. You will see it again and again. So, at this point, I could go and develop completely systematically the theory of tensors. Before I do that, what I would like to do is just do a little bit of an aside to discuss in a bit more detail the structure of coordinate transformations in flat Minkowski space. Before I do so, let me pause and see if there are any other questions. Okay. So, in general, the metric eta mu prime, which is eta mu nu times dx mu by dx mu prime, dx nu by dx nu prime, is not given by the constant matrix with entries -1, 1, 1, and 1. So, for example, we saw in this very simple case of flat space-time, whereas the metric is given by the constant matrix in Cartesian coordinates, it's given by the diagonal but non-constant matrix with entries 1 and r squared in polar coordinates. So, in general, the metric will not be, even though the metric takes the form of a constant matrix in in Cartesian coordinates, it's not a constant matrix in other coordinate systems. For example, on your problem set last night or yesterday, you showed this fact is responsible, for example, for the Coriolis and centrifugal forces. One can view, if one wants to be particularly perverse about it, one can view the existence of the centrifugal Coriolis and Euler forces as arising from the fact that you are studying Newton's laws in a rotating coordinate system rather than in a Cartesian coordinate system. That's something that we'll return to in a bit. I believe you showed this only for the centrifugal force in your problem set yesterday, but it's true for all of them, as I could have asked you to show. And maybe I will, if I'm feeling particularly cruel. However, it could be that something very special happens. So, there may be special coordinate transformations which leave the form of the metric unchanged. So obviously, that is not going to happen in the generic case, because these Jacobian matrices, dx mu by dx prime, will not be trivial. You know, there'll be some complicated functions, some horrific matrices. But there could be some very special cases where the metric is left unchanged. We have a name for those coordinate transformations. Those coordinate transformations are known as isometries. And they are precisely the symmetries of the underlying space-time. So if you think about it, what is a symmetry? A symmetry is a change of coordinates that leaves all of the physics unchanged. The fact that physics in this room is rotationally invariant is a consequence of the fact that any physics experiment that I do doesn't depend on whether I use a coordinate system which is aligned with the walls of the room or one which is rotated by some amount with respect to the walls of this room. So, as you all know, symmetries are deep and important concepts in physics. And when we're studying relativity, special and general relativity, to understand the symmetries of space-time, we need to understand those coordinate transformations which leave the metric of space-time unchanged. So, it's interesting and important then to ask what then are the isometries or the symmetries of flat Minkowski space. Isometry, I should mention the word isometry is simple to understand. Iso means the same, metry means metric. So it just means same metric. I guess that's probably obvious. Okay, so in Cartesian coordinates, eta mu nu is given by the constant matrix -1, 1, 1. And the question is whether there is a new coordinate system where eta mu prime, which is given by eta mu nu, dx mu by dx mu prime, dx nu by dx nu prime, is also equal to minus 1, 1, 1, and 1. So the first thing that you see is that the Jacobian matrices, dx mu by dx mu prime, will need to be constants in order for this to be the case. Now, the simplest way that could happen is if they're constants that are given by the identity matrix. For example, let's say that we have coordinates x mu prime which are related to the x mu's just by a shift, just by some translation. Well, then dx mu is equal to dx mu prime. Those Jacobian matrices are the identity matrix, and so these will be isometries of the spacetime. The metric will be left unchanged. So what does that mean? That means that the metric of flat Minkowski space is translation invariant. Okay, that's good. That's hopefully not such a surprise. We're used to translation symmetries, both spatial translation symmetries and time translation symmetries in physics. Let's see if we can recover other pieces of physics by thinking about the symmetries of the Minkowski metric. So a more interesting case would be where x mu is related to x mu prime by multiplication by some constant matrix. So x mu prime here is a set of 4 quantities, which we could arrange into a column vector if we like. And then you could imagine multiplying that column vector by a 4 by 4 matrix that I would call lambda mu nu prime. I could call that nu prime index mu prime if I want. Should I call it mu prime? It doesn't matter. They're dummy indices which are summed over, so you could call them whatever the hell you like. It doesn't matter. Let's call it mu prime. So, for example, you could imagine taking the set of 4 Cartesian coordinates and multiplying them by a constant 4 by 4 matrix. Then how would the metric look in this new coordinate system? Well, it would be equal to eta mu nu times lambda mu prime, lambda nu prime. This matrix lambda is just the Jacobian matrix. Take dx mu by dx mu prime in this equation, and that will be clear. Now, you may have noticed that I have been careful at this point not to use matrix notation. It's sometimes a little easier, however, to think about formulas like this in matrix notation. In general, many of the formulas that we'll encounter in this class involving tensors, coordinate transformations, and so forth cannot be written in terms of matrices, vectors, and the familiar objects of linear algebra and vector calculus. But when you can write formulas using matrices and vectors, it's often very useful to do so, at least with regards to applying your usual intuition from linear algebra. So what I'd like to do is write this formula in the familiar language of linear algebra. So, for example, if you have an object with a upper index, v mu or x mu or something like that, it's useful to think about the components of that vector sitting inside some column. So v mu would be v0 up to v3 or vd minus 1 if we're in some number of dimensions different from 4. And a matrix is an object with two indices. So an object with two indices, one upper and one lower, can be arranged into a 4 by 4 matrix. So the different rows and columns of this matrix would package together the different entries of the matrix lambda mu nu. So lambda mu nu is the symbol that we use to refer to those 16 quantities. But of course, we could package them together in a matrix if we like. And then, for example, lambda mu nu times v nu is just the usual formula for matrix multiplication. That's something that is probably not... Oh, I'm sorry, I mixed my metaphors here. I used 1 up to d in one case and 0 up to 3 in another case. So let's try and be consistent here. Let's just call everything 1 up to d. So let's see if I got this right. Yes. If you look at this, you will now see that lambda mu nu v nu is precisely the same thing as the matrix lambda acting on the vector v through the usual action of matrix multiplication, and it's the muth component of that. So the operation of contracting a lower index of one of a matrix with the upper index of a vector is nothing more or less than the usual operation of matrix multiplication. Likewise, we could define, if we have a symbol with a lower index, we could write that as a row vector rather than a column vector. And so one could think of that as the transpose of a column vector, if you like. But then v mu lambda mu nu is just the same thing as lambda acting on that column vector in the only way that a matrix can act on a column vector, which is multiplication from the right rather than multiplication from the left, and we've taken the nth index. So that's also matrix multiplication. And then one can write down more complicated formulas. So let's say that I have two matrices, lambda and, I don't know, what's another good name for a matrix? M. So if I have two matrices, lambda and m, so then lambda mu nu, m nu rho, so those are two matrices, each of which contains 16 components, then that is just the matrix multiple lambda times m, and it's the mu rho component of that. So that's also matrix multiplication. And finally, one could then ask what happens. So if I have an object lambda with two indices and an object, one of which is an upper index, one of which is a lower index, and an object m with two indices, one of which is an upper index and one of which is a lower index, there are two possible ways I could sum those indices together. I could either sum the second index of lambda with the first index of mu, as I have done here, which gives me normal matrix multiplication. Or I could sum the first index of lambda with the second index of m. And then you would have to ask what you get. And I will let you work this out for yourselves. But it turns out that what you get is not the usual matrix multiplication, but multiplication with a transpose thrown in. So the action of matrix transpose is the thing that interchanges the first and second indices. If you think about that for a few minutes, that should be clear. if you think about the way that I've written this matrix lambda mu nu here in explicit matrix form, interchanging the first two indices is equivalent to taking the transpose of the matrix. So this guy here is the matrix lambda transpose times M, and it's the new row component. Yes?
Can you just switch out lambda and mu to get the same thing as you have before?
Yeah. Let's see. Yeah. So it's also M times lambda with new row components. Yeah. Right, because interchange, yeah. And I think if you work it all out, the transpose stuff, that should hopefully all work out. Yes?
How does commutativity work?
Well, good. Okay. So matrices, of course, don't commute with one another. You should remember, however, that when I write a symbol like lambda mu nu, I'm writing out the indices explicitly. And so lambda mu nu is just a set of 16 numbers. Numbers commute with one another. One of the advantages of using this abstract index notation, where we just write out indices rather than writing out, symbols with vector symbols on top of them, is that you never have to worry about whether lambda mu nu commutes with M mu nu, because they're both just numbers. They're just 16 different numbers that are labeled by indices. Of course, the other reason why we use this is that we're very quickly going to be discussing objects which have more than two indices. And whereas it's pretty easy to visualize in your mind something with one index, it's a vector. Two indices is a matrix. Three indices, that gets a little tougher. Four indices is even worse. And we will, of course, make good friends with things that have four indices in the next few weeks. Yes?
So they could be reversed, and we figure
out. You just need to, whenever in doubt, just write it out. Right? I mean, what is this guy here? This is a set of 16 quantities labeled by mu and rho, where mu runs from 0 up to 3 or whatever it runs over, and so does rho, summed over nu. So, if you ever are confused, you just write it all out. Write all 16 of them out. Each one of those 16 components is the sum of four terms, one of which is lambda 0, 0, m 0, 0, plus lambda 0, 1, m 1, 0, and so on and so forth. Trust me, if you start writing out these 16 terms, each of which is the sum of four terms, before you get to the end of writing out those 64 terms, you will have figured out exactly what the compact way of writing this formula is. At some point, there's nothing to do except just start writing these things out, and it's perfectly clear. You got some practice with it for your last problem set. You will get more with your next problem set. Other question, yes?
I don't think that's quite right.
I'm sure it's wrong. Yeah. Did I make a mistake?
Well, first you put the index on M, and then you change.
Oh, I guess I need to write new row here, don't I? So which one?
But you change the index. You change the order. You change the order of the indices, and then you change the sum of them. So that's the same as.
For which one?
When you pass from the first line to the second line.
So these two, this line and this line, these two lines are not at all related.
Yes, but when you switch the indices, you switch lambda to lambda transpose.
Yes.
Not only this is the indices, you change the index to sum over.
Yeah, I can sum over whatever index I like.
But in the first example, you were summing.
Yeah.
You're summing over different indices.
Yes, that's correct. That was intentional. Right? I mean, if I have two objects, each of which have one upper and one lower indices, there are two different possible sums two possible different objects with two indices I could create out of that. One of which has, where I sum over the second index of the first object with the first index of the second object, and one of which where I sum over the first index of the first object with the second index of the second object. There's no particular reason for those two things to be the same, and indeed they are not.
I think you can mix of the chance. That wouldn't make one reach in the chance because you just switch the order of multiplication.
Okay, I challenge you to check this then. Okay, this is a homework problem. This is not a graded homework problem, but rather a homework problem that you will do for your greater education as physicists. Work this out. See what it is. Yes?
So that multiplication should be m lambda, but
Which
so your second one should be m lambda rho mu, or both of those should be transposed. They should be written as mu rho. Because if you just switch the order m rho mu, lambda mu, it looks exactly the same as the previous line. So it should have the same structure.
Okay, let me stare at this for a minute. It's always possible, I do occasionally make mistakes. It happens extremely rarely. Let's see. Did I get this one wrong? Yeah, it's the whole thing transposed, isn't it? I guess you're right. Is that what you were trying to say?
Yes.
Okay. Okay. Sounds good. Any other questions? Yeah. As I said, I will frequently make mistakes of this nature to make sure that you're keeping up with me. So congratulations. Test passed. Yes.
Actually, can we go back?
Sure.
Like, for example, you write the mu with the subscript.
Yes.
You're keeping track of the minus signs from contracting with mu nu.
I have not told you anything about contracting with G mu nu. That we have not reached that point in this course. We will reach that next week. When I write V with a subscript mu, I just mean an object with a lower index. We will, don't worry. So far I have not, so an object with a lower index is just something with a lower index. Okay. I'm telling you this for your future education. Someday, perhaps in this class, we will learn to lower and raise indices with the metric. I can only dream and hope that such a day will arise. Any other questions? Good. Okay, let's return then to our question of the isometries of flat Minkowski space. So we are looking then for constant matrices lambda mu nu such that eta mu prime, which is given by lambda mu prime, lambda nu prime, eta mu nu, is just equal to the constant matrix minus 1, 1, 1. Or if you were to write this out in matrix notation, I invite you to check that this is the same as the statement that lambda is a 4 by 4 matrix, which obeys the following formula. So if you take the constant matrix with diagonal entries minus 1, 1, 1, and 1, and you conjugate it with the matrix lambda, multiplied by lambda and lambda transpose on the left and the right, then this matrix will be unchanged. So this sort of relationship should be rather familiar to you from your studies of linear algebra. It's, for example, the same relationship that is used to define the rotation matrices, which are the rotations of three-dimensional space. But here, this is the four-dimensional version in Minkowski space. So let's then ask what sort of matrices lambda would obey this formula. So the first sort of matrix that would obey this formula is a rotation matrix. So for example, if lambda is given by 1, 1, and then some 2 by 2 rotation matrix. So here C and S stand for cosine and sine. Maybe I'll write that out a little more explicitly. Cosine theta, sine theta, minus sine theta, cosine theta. Then what coordinate transformation does lambda lead to? So lambda is the coordinate transformation where we take y to y cosine theta plus z sine theta, and z to minus z sine theta plus y cosine theta. I'm sorry, minus y sine theta plus z cosine theta. So this, of course, is just a rotation. And so we see that indeed, as we should have anticipated, some of the isometries of Minkowski space are just rotations which leave invariant the line element. So that's perhaps not such a surprise. And indeed, one can check that this coordinate transformation leaves invariant the line element ds squared. And indeed, you can check explicitly that it leaves invariant, it only changes the y and the z coordinates, but it leaves invariant the combination dy squared plus dz squared. More interesting, however, are those isometries which mix the space and the time directions. So as you can see from this formula up here, they will look very similar to the rotations, except they will be slightly different because of that funny minus 1 instead of 1 in the first component of this matrix. So indeed, one can check that such a matrix will take the form cosh beta, sinh beta, cosh beta, 1, 1, for example. So here we just have coshes and sinches instead of sines and cosines. And so I invite you to check that this matrix obeys this formula up here. It's just a moment's work. If you stare at it, you can see explicitly that it happens. Okay, let's stare at it for a minute. Right? Okay, you multiply lambda times minus 1, 1. Then you multiply it as lambda transpose. Cosh squared minus sin squared is 1. Okay, so it works. And indeed, what does this coordinate transformation do? This is the coordinate transformation that mixes time and space. So lambda takes you to a new coordinate system. T goes to a coordinate t prime, which you could call cosh beta t plus sinh beta x, whereas x goes to sinh beta t, plus cosh beta x. Now, of course, in your previous encounters with special relativity, you learned about coordinate transformations that mix space and time. These are referred to as boosts, and they're the coordinate transformations that take you from the inertial coordinates associated with one observer to the inertial coordinates associated with another observer moving at constant velocity with respect to that observer. So if our original Cartesian coordinates were inertial coordinates with respect to an observer who was static, then this boost will take us to a new coordinate system that is moving with some constant velocity relative to that first coordinate system. And these two different types of coordinate systems are related by an isometry, meaning that the metric and the line element are left unchanged. And so you see then that the fact that in special relativity there is no preferred reference frame, there is no universal reference frame, is completely encapsulated in the fact that there is no preferred coordinate system that one uses to write the metric of flat spacetime. Indeed, you can check explicitly that if you let beta, I believe, be related to V by the following equation. So I challenge you to take this equation and plug it in here, and you'll see that this is the usual formula for the transformation of x and t when one boosts from a coordinate system to another coordinate system that's moving at a constant velocity with respect to the first coordinate system. And indeed, one can check explicitly that this coordinate transformation leaves invariant the metric, and in particular, it will leave invariant minus dt squared plus dx squared, which I remind you were the first two components of the metric of Minkowski space written in Cartesian coordinates. And the coshes and sinches appear because of that funny minus sign in front of dt squared. Question, yes?
Yeah, I think you pick up the minus sign. You're looking at a reference frame that's moving back.
Oh, is there a minus sign here, you're saying? That's certainly possible. Yeah, I didn't tell you how I was normalized. I didn't tell you what V was. V was minus the velocity, if that's the case. V is whatever it is to make this formula right. Any other questions? Excellent question. Not sure if I understood it, though. Any other questions? Good. So, just for your edification, let me throw out some words for you to listen to. So, there are 10 isometries of flat Minkowski space R3, 1. So we have 3 rotations. Those are the usual ones. And 3 boosts, because I can boost in either the x, y, or z direction. I can write down coordinate transformations that mix t with x, t with y, and t with z, just like I can write down rotations around any 3 axes. So these 3 rotations and 3 boosts combine, they mix to form 6 generators of what are known as Lorentz transformations. Which are those coordinate transformations that leave the metric fixed and also leave the origin of your coordinate system fixed. We have a name for the set of 6 Lorentz transformations. We usually call them SO3, 1. So, for example, you may have seen the rotation generators, the 3 rotations referred to as SO3. So the symbol SO31 is just a fancy name for the generalization of that notion to the Lorentz transformations of special relativity. And there are also 4 additional isometries of R3, 1. And so the 4 translations plus the 6 Lorentz transformations give you the full symmetry group of special relativity, which is known as the Poincare group, and is sometimes referred to as ISO 3, 1. Now, I don't think it's particularly important at this point for you to understand exactly why I use symbols like ISO and commas where they are and so on and so forth, but I introduce this to you for your education as physicists, because it's a language you may see again in the future. Yes, question?
I don't see why people do it necessary. Can't you just rotate between reference with rotation?
Indeed. Well, when you say, what do you mean when 3 boosts are not necessary, but let's put it this way. If I handed you any 2 rotations, you could commute them to get a 3rd rotation. Okay? If I handed you any 1 boost and the 3 rotations, you could take those rotations and 1 boost and rotate that boost around to get the other boosts. So this is just a statement that these Lorentz transformations form an interesting algebra. It's an algebra I'm sure I'm going to make you work out on some problem set in the future. It's an algebra that's very similar to the algebra of rotations in 3 dimensions. But I don't understand. But they are necessary in that. I don't know what you mean when you say they're not necessary.
Well, it just seems that the number 6 is a little bit arbitrary.
What?
Well, the group has an infinite number of elements.
The group has dimension 6. So let's think about it this way. The rotation group has an infinite number of elements, but it's generated by 3 generators. There are 3 generators of rotation. Or another way of saying that is an element of the rotation group is uniquely specified by 3 angles, the Euler angles. Likewise, an element of the Lorentz group is uniquely specified by 6 numbers, the special relativistic version of the Euler angles.
But if you express any Lorentz transformation, it's just using just 1 boost generator.
Absolutely false. You could express a Lorentz transformation between the 2 coordinates t and x using 1 generator, but between t, x, y, and z, you need 3. A boost in x, a boost in y, and a boost in z.
But can't you just use a combination of rotation generators and the boost generator in x to put the boost in all the...
No, you need 6. Let's put it this way. Let's do some counting. Okay. Let's stare at this equation right here. And let's ask how many parameters it will take to uniquely specify the matrix lambda. And I claim that if we stare at this equation, we should be able to see that it takes 6 parameters to uniquely specify the equation lambda. So let's see that. Lambda is a 4x4 matrix. A 4x4 matrix contains 16 elements. This equation is an equation for a symmetric matrix because eta mu nu is a symmetric matrix. And when you take a symmetric matrix and you conjugate it by an arbitrary matrix of in the form lambda matrix, lambda transpose, you preserve the fact that the matrix is symmetric. So this is a symmetric matrix equation. This is a matrix equation which is automatically symmetric. And a symmetric matrix has 10 degrees of freedom. So we have 16 degrees of freedom in lambda and 10 constraints on those 16 degrees of freedom. So that means we require 6 parameters to uniquely specify lambda. This is exactly the same. This is exactly the same counting that one would do if one wanted to count the number of rotation generators. So, no, that's a very good question. I shouldn't have said it's absolutely false. That's I haven't had enough coffee or something. But that's a very good question. But my claim is that you will need 6 parameters to uniquely specify a Lorentz transformation. And that's reflected by the fact that you can find 6 linearly independent generators of these rotations. So on your next problem set, for example, you'll work out explicitly what the generators are of the rotation algebra. Now, I haven't told you exactly what it means for one of these isometries to be generated. That's something that we'll discuss later on. But yeah, so these boosts are all necessary. Yes. I mean, they do obey non-trivial relationships with one another. So the commutator of 2 of these will give you a third. So for example, the commutator of a boost with a rotation gives you another boost. The commutator of a rotation with a rotation gives you another rotation. And the commutator of a boost with a boost gives you a rotation. That's actually something that you may not have learned, but it's pretty cool. If you do a boost and another boost, and then you do the same 2 boosts in the opposite order, and then you subtract them, you actually get a rotation. So they're related by some non-trivial algebra, which is a generalization of the usual rotation algebra. Question? Yes?
What were the transformations?
Good question. So I've been a little sloppy in that I'm only discussing continuous symmetries. Continuous symmetries are the most useful symmetries because they lead to conserved quantities and drastic simplifications in all sorts of physics. There are also discrete symmetries. So, for example, there are various reflection symmetries, parity symmetries, time reversal symmetries, and so forth that also leave the Minkowski metric invariant. Sometimes people will refer to SO3, 1 plus and SO3, 1 minus, depending on whether you throw in a parity transformation or something like that. Yes, you can clearly see, for example, that t goes to minus t will leave dt squared invariant, right? Because it takes dt to minus dt. dt squared then doesn't change. So, yes. So clearly that would be a time reversal symmetry. Likewise, you have all of the various parity symmetries. So yes, one should throw those guys in as well. Some of those guys can be obtained by rotations, and some of them cannot. I leave that as an exercise for you to puzzle out. For example, it turns out that if you do a simultaneous reflection in two of the elements at once, you can obtain that as a rotation by a rotation or a boost. I'll let you try and figure that one out for yourselves. It's a true fact. Any other questions? Good. Yeah, please feel free to ask as many questions as frequently as you like. Okay. So, the coordinate transformations that we have discussed above are the simplest sorts of coordinate transformations possible. So these are the simple coordinate transformations. Which leave the metric unchanged. And in particular, they are the coordinate transformations that take you from one inertial coordinate system to another inertial coordinate system. They're the coordinate transformations that either involve a rotation or a boost with constant velocity. But gravity, of course, is more complicated. And in particular, as we learned in our discussion of the equivalence principle, gravity is related to acceleration and non-inertial coordinate systems. So what we need to do is we need to find a way of writing the laws of physics in a way that is invariant, not just under those simple coordinate transformations that we have described above involving constant velocity, reference frames, and so forth, but under any random sort of coordinate transformation that might involve accelerating reference frames and so forth. So we need to deal with more complicated coordinate systems, and in particular, this will lead us to the subject of tensors and tensor calculus. And that is the subject that we will turn to now, and that I would like to spend the last 10 minutes or so of class introducing. Before I do so, are there any questions? Okay. Now, you've surely encountered tensors at various points in your physics career, but it is most likely that you have not, except in a few very special cases, actually heard them referred to as tensors. In your electromagnetism classes, you probably have encountered either the electromagnetic field strength tensor or the stress tensor. If you took a particularly good class on mechanics, you might have seen the inertia tensor. if you took a good class in engineering, you might have seen strain tensors and so forth. But the idea of tensors is, in fact, very, very simple. And much of what we will do, at least in the beginning in our discussion of tensors, is simply rediscover a lot of things that you already know, albeit in a slightly more sophisticated and general language. So what is a tensor? Well, I don't want to start by giving you some fancy highfalutin definition. So let's just give a bit of a gentle introduction. So a tensor is a generalization of the notion of a vector or a matrix to objects with more indices. So, before giving you the most general definition of a tensor, let me just start with some simple example of tensors that you already know. So let's consider a d-dimensional manifold. So if we take a particular patch of this manifold, a particular region inside this manifold, then that region can be smoothly labeled by many different coordinate systems. And so let's say that it's smoothly labeled by two coordinate systems, x mu and x mu prime. So a tensor is an object which transforms in a specified way under the coordinate transformation when we rewrite physics in terms of things in the x coordinates in terms of the x prime coordinates. And the simplest tensor is what is known as a scalar. So a scalar is an assignment of a number to each point in M in a way which is independent, of course, of the choice of coordinate system. So, for example, if you have a scalar f, say, then you could write in the x mu coordinates, you could write f as a function of the coordinates x mu, and in the x mu prime coordinates, you could write f as a function of the x mu prime coordinates. And if f is a scalar, then these two functions will be related in a particular way. So if the coordinate transformation says that x mu prime is a given function, say x mu prime is a given function of the x mu's, then f of x mu prime is given by f of x mu prime regarded as a function of the x mu's. So, if you know what I mean. Or let me put it this way. Perhaps the way I should write it is that f of x mu prime is f of x mu with the x mu's regarded as functions of the x mu primes. And so we often say that f is invariant under coordinate transformations. Now that does not mean that f has the same functional dependence on x1 and x2 as it does on x1 prime and x2 prime. a scalar function in Cartesian coordinates does not depend on r and theta in the same way that it depends on x and y, right? But it does mean that it transforms in a specified way under coordinate transformations. Namely, it transforms exactly how you would think it transforms under coordinate transformations. You replace x by, you just use the formula for the x mu's in terms of the x mu primes. Yes, there was a question. M is the manifold. Sorry. The d-dimensional manifold M. Sorry. Good question. Thank you. Any other questions? Okay. Now, the notion of a scalar is something that is rather straightforward. And we have a special name for scalars. A scalar is known as a 0, 0 tensor. Okay. That should give you some idea of where we're going with this. So now what does it mean when I have numbers aside from 0 and 0 inside those parentheses? Well, the next example of a tensor which you have encountered in your lives as physicists is that of a vector. So a vector is somewhat more complicated than a scalar. So a vector is a set of d functions which we call v mu, where mu is an index that runs from 0 up to d minus 1 or 1 up to d, depending on the dimension of the manifold, which transform in a particular way under coordinate transformations. So under the coordinate transformation, where we replace x mu by x mu prime, they will transform in the following way. So if the vector is given by the d functions v mu, regarded as functions of the x mu in the x mu coordinates, then in the prime coordinates, we want to write down v mu prime as a function of the x mu primes. And that is not given just by regarding x mu as a function of the x mu primes. So it's related to v mu regarded as a function of the x mu's, regarded themselves as functions of the mu primes, but multiplied by a Jacobian matrix. So at this point, this is just a definition. We define a vector as a set of d quantities associated with each coordinate system, which transform in a particular way when we make a change of coordinates. And this vector is a particular sort of vector. So this is sometimes referred to as a contravariant vector, or simply as a 1, 0 tensor. So this object here is just the usual Jacobian matrix that we have encountered many times already in this course. So this transformation equation can be written in the language of vector calculus. Just as the statement that v prime is equal to the Jacobian matrix times v, where J is the d by d matrix of partial derivatives given by this expression in the parentheses here. And this is just the natural generalization of the notion of a vector from vector calculus to a more general set of coordinate transformations. So, for example, if you're in 3 dimensions and you have some column vector, and you do a rotation of your coordinate axes by some matrix J, then this equation here just describes precisely how the components of that vector change when you write them in that new rotated coordinate basis. So we'll discuss more vectors and tensors starting next class. So let me end here unless there are any questions. No questions? So see you Thursday at 4 p.m. for our very special makeup class. I'm really looking forward to it. We'll all have a great time. Thank you.